Welcome to the office. We want to take a look at a few theorems here. So a couple theorems and a corollary, actually, but this should be pretty quick for us. Just trying to grab onto a couple of key results for the chapter, for the section here. So this first theorem that we want to take a look at is actually, I mean, it's not explicitly a reference back to things that we've already done, but what we've already done plays a significant role in us understanding kind of what's going on with this theorem. So if you haven't watched all of the videos or didn't follow along with all of them, I would encourage you to reflect a moment, or possibly after you watch this video, on, let's see here. I would encourage you to reflect on this example here. We looked at the equivalence relation x is related to y if and only if phi of x is equal to phi of y. And then we took a look at the left coset of the kernel and found that to be the equivalence class containing A, and that life was good. Okay, and that's essentially the same thing that we want to look at here. Oh, look, phi of x is equal to phi of A. So this is the equivalence class containing A under exactly that relationship that we were looking at earlier. And that happens to be also exactly the preimage of phi of A based on the definition of phi of A. Okay, so phi inverse of A, rather. Phi inverse of phi of A. Ooh, right, there's that composition there. This is all, whatever this gives me, phi of A. When I go back into G, I'm looking for all the things that give me that as well. So this is kind of a crazy notation. This we can see as the equivalence, I'm sorry, the equivalence class. All the things that are related to A, and then this is just another way that we can say that. And we already looked at the fact that this is the left coset, A times the kernel. So H is the kernel here, right? This is A times the kernel. But the work that we showed in our previous example is actually exactly the same work that it would take to show that this is the right coset. So reflect on that and see if you can verify that, hey, look, it is the same, because the only thing that mattered there in terms of being able to, right, we went from here to here. That was the tricky part, if you want to call it that. And it just took this note that we can express every element in G as A times something. Okay. And we're just looking for the elements that work out to give us this. And so you just want to be able to recognize that you can write every element as something times A instead of A times something. And that's the only adaptation that you would have to make to get that this is exactly the right coset of H, the right coset of the kernel. So what that means for us is that we have that the left and right cosets are the same. Now, this property itself is very important to us. It's important in, right? We're going to use it in later sections, and it is so important that we can actually, on the next page, oh, I'm sorry. I guess it's the page after that. We actually give a name to this property. When we have that the left and right cosets are the same, we say that that subgroup is normal. It is a normal subgroup. All right. So if this is a group homomorphism, based on what we saw in our last theorem, that the left and right cosets are the same, then this indeed is a normal subgroup, right? So this really isn't even a corollary. It's just a restatement of the previous theorem, right? The left and right cosets are the same. It's a normal subgroup. Wonderful, fantastic. It's going to be very important information for us, normal, and this particular example of a normal group. We'll want that. Okay, so that's the main key takeaways as we move into the next sections, right? We want our understanding of kernels. We want to know what they are, how to find them, that sort of thing. Even if we're not very good at finding them, we want to have a good understanding of what a kernel is, a good understanding of what a homomorphism is and how to find one, that sort of stuff, right? Exactly the things that we took a look at in this section. The only other thing that we want to notice is that, right, I've already made this connection between an isomorphism and a homomorphism. An isomorphism is a specific example. Now, if we have that, if we have an isomorphism, I already said it earlier, I think maybe in the first video for the section, that the kernel is just the identity in G. And that's all that we're saying here. If we have something that's one-to-one, then yes, the image of one element is going to be one element. So the pre-image of one element is going to be one element. Yeah, obviously, right? If it's one-to-one, or it's one-to-one if and only if that. Okay. So I suppose, right, that makes it very nice. We know that if the image is only one thing, that it's going to be one-to-one, or that if it's one-to-one, the image is only going to be one thing. But having just this specific example, that there's only one thing that gives us the identity, that one thing will actually determine everything else, that everything else must be one-to-one as well. All right. We don't really use that. It's just a nice thing to observe. I don't even think there's any homework problems on it. So cool. Try to remember it. It might come in handy at some point. But that's all that I really wanted to share for this video. So thank you for your time and attention here in section 13 in our discussion on homomorphisms. Have yourself a wonderful day.